That way, I always remember. That is so loud. Holy mackerel. All right. I'll be back in 5 minutes. That is so annoying. Too loud. All right. All right. You're familiar with
don't know if physics Newton's the less different than physical science. What I would say. All right, let's see. Well, now we have a fun now. So the force concept is the first chapter is just.
So it's about Pythagorean theorem.
Sort of,
This is
yeah.
a total force, what's our force in one direction?
Yeah.
Direction.
We can also do it in two dimensions. One dimension. Okay. And so, actually, let's go back. Okay, are you familiar with these boxes? That's the one. Okay, so there's a lot of stuff like that.
So it's the fact that you pull up and gravity pulls the
Yeah. Okay. There's a lot of stuff like that. There, that's more. Or you see those before, right? You touched on those and stuff. I would go through it and start having issues. I just started doing the homework and if you start having issues, look at the book in the lecture.
Okay.
That's how I do it.
All right. Back to physics. Chapter 4 homework. How is it going for you guys? Anybody have any questions they want to do together?
Number 8.
Number 8. Okay, does this look like the right one?
Yeah.
What is the weight of an object with 16.6 kilograms mass, I guess, right? So we want to know the weight. How do we do that? What did you try?
It just don't make sense.
Okay, what was your answer?
I didn't have one because it's just like, is it 16.6 kilograms of weight?
No, that's the mass. Remember, this is one of the things we talked about at the very beginning of the class, where mass is actually the amount of stuff, right? But weight is the force that the Earth pulls on that mass with. So weight is
Mass times gravity, right?
mass times gravitational acceleration.
And then your unit would be your newtons, right?
Newtons, because that's Newton.
Would you write out the word newtons for this website or just the capital N?
Good question. Let's find out.
I've been doing
We'll try capital N and see if it works. Capital N works. Let's see if Newton's works. They might both work. They have the option of doing more than one answer correct. They usually do. So Newton's orient works. So the way to calculate this is take your mass and multiply by 9.8 meters per second squared, and that will give you kilogram meters per second squared, which is newtons, and then you're good to go. And the direction that it pulls on, downward, right? So. Anybody else have a problem they would like to? So, thing to remember, mass and weight are not the same. The mass is the amount of stuff. Weight is how much force the Earth pulls on that stuff towards the center of the Earth. Now, an interesting way to distinguish them is through examples of how these things would behave. For example, if you had a car on the moon that was 1,000 kilograms of mass, and it had 0 friction wheels, so pushing the car didn't require you to overcome any friction in the wheels or between the wheels and the ground or anything else, then you would be able to push that car on the Earth just as well as you were able to push it on the moon. However, it would be much more difficult to lift on the Earth than it would be to lift on the moon, because to lift that car on the Earth, you have to overcome all the gravitational force that is pulling that mass towards the center of the Earth. But on the moon, the gravitational force that pulls a car towards the center of the moon is 1/6. It has less gravity. So it's the same to push it, but less to lift it on the moon.
Can we look at number one, just want to make sure I kind of have the right idea? So is force always measured in newtons?
You can also measure force. There are other units for force. Another one is pounds.
Okay. So with this one, when it's asking about the horizontal force, I would, your net force equals your acceleration times mass. So you just make 2.1 times 0. Obviously, the numbers are different.
Yeah.
The numbers multiply.
So this is your acceleration, this is your mass, and the force is equal to acceleration times mass.
Okay, and then anytime that you have like an acceleration times a mass, I guess like you have meters per second squared times kilograms or grams or whatever, that would be newtons, right?
That's right, because newtons are the same as kilogram meters per second squared. Cassidy, you had a question?
Yes, I did. Number 11, part A.
Number 11, part A, Big Bubba. Okay. Let's see, he goes to another planet with gravity different than Earth. So he has a mass of 114 kilograms on Earth. Remember that, what is mass? What is the definition for mass? Do you remember that, Cassidy? The definition, the official definition for mass is how much matter you have in an object. So if a particular object is got 5 kilograms of iron in it, that means it has 5 kilograms of iron atoms. 5, and that's almost like counting. And it's not a weight, it's just it's an amount of iron. That amount of iron doesn't change just because you take it to the moon, right?
No.
It doesn't change. The amount of iron stays the same. So it turns out he has the same mass on the moon. However, the moon and the Earth pull on that mass differently. Because the Earth is bigger, it pulls harder on the mass. And because the moon is smaller, it pulls not so hard on the mass. So his weight on the Earth is much different than the weight on the moon. His weight on the Earth is this 114 kilograms times the acceleration from gravity on the Earth, which is 9.8 meters per second squared. However, the planet that he's going to, it only has an acceleration of 6.6 meters per second squared. So then you multiply his mass times this 6 meters per second squared to get his weight on this other planet. Does that help?
Yes.
Okay.
I mean, I finally got the right answer on number 5, but I still kind of didn't get it. Maybe it just didn't click, but.
A constant non-zero net force results in. So this force is constant, it's not changing, it's always pushing or pulling at the same amount in the same direction. And it's not a zero force, so it's not equal to 0. And it's a net force, which means that it has some value. That's all that they're saying. So it's a net force, meaning it's the sum of all the forces on this object. So what this question is saying, you have a force that's pushing or pulling in the same direction with the same amount of force all the time, and it's not 0. What's going to happen to this object?
Constant velocity, right?
What does force do to an object?
Accelerates. So it's a constant acceleration.
It's a constant acceleration because force causes acceleration. It will not be a constant velocity because forces cause acceleration, which means not constant velocity, right? It's not going to be an object at rest because an object at rest is a constant velocity of 0, which is not an acceleration. It's not a constant motion because a constant motion is not a acceleration. So it's got to be a constant acceleration. Now, if it was a changing force, then it would be a changing acceleration. But since it's a constant force, it's a constant acceleration. So the only two that are even possible is this constant acceleration and changing acceleration. But since the force is constant, the acceleration has to be constant. And the way to think about that really is like this. The equation is force, which is a vector, equals mass, which is a scalar, times acceleration, which is a vector. This equal sign means that this thing is the same as this thing. This left-hand side is the same as the right-hand side. But since the only vectors on the left and the right side are the force and the acceleration, and if the force, let's say the force over here is this, right, is this arrow, and that means the acceleration on this side has to be in the same direction. It doesn't have to be the same length, because the mass could be a bigger or smaller number, which would make this length bigger to match this one in the end. So in other words, this vector has to equal this mass times this vector, right? So if this one is constant, then this one has to be constant. If this one is changing, then this one has to be changing because the mass doesn't change, right?
Look at number 2, please.
And if you didn't have a force, you couldn't have an acceleration because this would equal 0. That would mean this would have to equal 0.
Mm-hmm.
Is that good?
Yeah. Did someone else have a question?
Okay, what's your question there? Go ahead. Number 2. 36 Newton force applied to a 10 kilogram object, accelerated towards the right. The object encounters 19 newtons of friction. Okay, so
So I have a formula that says acceleration equals net force over mass, right?
that's right.
And so would I just take the acceleration of the object in one direction and then the acceleration of the friction and average them?
Nope. This is what it says. Net force, which means the sum of the forces, you add them up, right? Equals mass times acceleration. And we're in one dimension, so we don't have to worry about the vectors here. We just have to worry about the signs. So they told us the mass. We know what the mass is. And we know what the forces are, but we don't know what the acceleration is. What we need to do is we need to add the forces together. What forces do we have? Let's draw them. We have the force pushing this thing to the right. That's our pushing force. We'll call it force push. And then we have a friction. Now, which direction does friction always point?
Opposite direction.
opposite the direction of movement, right? And we're going to assume that this is going to move in the same direction that we push it. So that means the friction is going to move opposite that, like this, frictional force, which we usually write as a little f. So which one's positive, which one's negative? Well, let's call this way the positive x direction, right? So this one's the positive force, and this one's the negative force. And if we're going to add this up, what this net thing here means is the sum of all the forces, right? In other words, force 1 plus force 2 plus force 3, and so on. Dot, dot, dot equals the mass times the acceleration. Oops. So we're going to add the forces. We're going to add force P plus force friction. Force P is positive, so we write it as force P, and they've given us that number. And then we're going to add the friction, which is a negative one, so we end up subtracting force friction. And those are the only forces we have, so that has to equal our mass times acceleration. Right? We divide by the mass on both sides to get a formula for the acceleration. And we end up with force P minus friction equals over mass equals acceleration. And that's how you solve that one.
Okay, so force minus friction over mass.
Push force minus the frictional force over the mass will give you your acceleration in that case. Cassidy, did you have another question?
Yes, I'm just not sure which one to ask, I suppose. Oh, 18's a good one.
Okay.
Sorry, I have people in my house currently, so any background noise is from that.
No worries. Okay, so the free body diagrams above, which of these objects could be moving to the right with a constant velocity? So remember that it's the sum of the forces that makes something accelerate. So if we add this force, so we're looking for to the right. So we're only looking for forces moving left and right. So if we're going to assume that to the right is positive, to the left is negative, then this free body diagram would show an object that has 20 newtons of force to the right and 20 newtons of force to the left. That's a positive 20 plus a negative 20, which equals 0. So it can't be A because there's a 0 force in the right-hand direction. This one here would have 20 newtons to the right, which is positive 20, 15 to the left, negative 15, positive 20 plus a negative 15 is positive 5. So this one could be moving to the right. This one has no force to the right or to the left, so this one couldn't go anywhere to the left and right. And this one has only 20 newtons positive to the right, so this one could also be moving to the right. So in this case, it is A and D.
So if the force
No,
is
let's see. Which of the objects could be moving to the right? Oh,
B and D.
there's one more. That's, what did I say? I said, I said A and D. But it's even wrong if I do this. And because there's one more, because this is one of those trick questions.
Oh, okay. Because that's what I did, and I got it wrong. Yeah.
So if it's moving to the right, oh, sorry. It's a constant velocity, not a constant acceleration. So it can't be B or D. B and D are going to move to the right not with a constant velocity, but with a constant acceleration, right? Because these ones are forces to the right. We're looking for ones that actually have 0, so it's actually A and C. We want to have 0 force to the left and right because it's constant velocity, not constant acceleration. And I don't know what I said out loud, but I was thinking constant acceleration, so I was looking for forces. But C and A are the ones that have no forces to the left or right. They have a total force left and right of 0, so they can't be accelerating left or right. But they can be going 0 or a constant velocity. So that one should be the correct one. Does that make sense, how that works?
So so 0 is the constant velocity.
So a 0 force in any particular direction means that one of two things can happen. If you have no force to the left or the right, then you can have either an object that is at rest or moving at a constant velocity either to the left or right. Okay? And if we're talking about moving to the right with a constant velocity, then we need a zero total force left and right. So this one has a negative 20 plus 20, so that's zero left and right. And this one has no forces left and right, so this one is zero left and right.
Okay.
Okay? If you're looking for a constant acceleration, the only two that could have constant acceleration are the other two, B and D.
Maybe that's what I was thinking of. Yeah, probably.
That's what I was thinking to begin with, so.
Just because if
Yep.
you look at 15-inch from the
15. The net force on the box, 84 newtons left, A, 446 newtons, B, 3047.
So basically, what it's saying is if it's moving, it's to the left, and we know that like the force A is, the overall net force is to the left, and the force A is moving to the left, and like.
So let's look at this problem in a drawing really quick. We have these four forces, and I'm not sure if this is going to be exactly the same as it is in the problem, but it'll be the same idea. Oops. We have these four forces. They're not necessarily equal forces at all, but they do tell us the value of two of the forces. Oops. So they tell us the value of force A and B. So they say maybe this one is equal to 5 newtons. And maybe say B is equal to 7 newtons or something like this in magnitude. If you're talking about direction, then this is also equal to negative 5 newtons, and this one's equal to positive 7 newtons, right? And it might be good to just remember to just draw those values in, draw the signs in, so that you remember that if this thing is moving, let's say that this problem says that the acceleration of this object is to the right. It's to the right 2 meters, it's accelerating 2 meters per second squared to the right, or something like this. What do they tell us? Do they tell us the net force?
It says the net force on the box below is however many newtons to the left, and it gives me force A
Okay.
and force B.
So what it does is it tells us the total force or the net force. So the net force on this, which is add all these things together, and you get a net force that is in some direction. In yours it says to the left, it could say to the right or whatever else. But let's say it's just to the right, 2 newtons, positive 2 newtons. Well, net force means that you add all the things in the y direction and all the things in the x direction, and then you get a total vector. The total vector is to the right. So can we have any up and down force?
So you can't. So the B one would have to be exactly opposite.
That's right. Because the total force, when we add it together, is only to the right, these two have to cancel. They're the only ones that can cancel each other out so that there's 0 up and down. So this one has to equal negative 7 newtons. So that one's easy. And then this last one, you have to have a negative 5 Newton force, and you have to add to it a force in the c direction that gives you a positive 2 newtons total. So in other words, negative 5, which is A newtons, plus c newtons has to equal plus 2 newtons. So you do the math, you add 5 to both sides, you get c has to equal plus 7 newtons. And that's how you do that problem. Doesn't matter which way your problem tells you things are going. In the end, in this particular problem, in the end, since the final net force is going to always be either left or right or up or down, then 2 of these are going to cancel, and the other 2 have to add to be whatever net force they give you. Got it? Okay. Anybody else have one question? Any more questions?
I have no, but I figured I'd let somebody else take it.
Anybody else want to ask a question?
9.
Good to go? Okay,
Number
what are your other questions?
Number 12.
Number 12?
It's cards. Kind of like that cannon, I feel like.
Okay.
So they're all moving to the right, and then it has to use the active line, which would be negative.
What did I just do?
You can put it on the back button or something.
Okay. All the carts shown below are currently traveling to the right at the same velocity, each receiving a net force. Rank them from least to most amount of time it takes to bring to a stop. So if we look at one of our kinematic equations, there's a kinematic equation that will tell us if you're moving at a constant velocity, or if you're moving at a velocity to start with, and you're accelerated, how much time it takes you to stop. And that equation looks like this. V final equals V initial plus acceleration times time. Right? So, what are the things we know? We know the acceleration, and we know V initial, and we know V final, right? What's V final in each one of these cases?
0.
0. V initial is just the same V for everybody, just V. And then we have plus the acceleration is the thing that's going to change. That's going to be the variable. And then the time is the thing we're going to solve for, right? So if time's the thing we're going to solve for, let's go ahead and solve for it. We're going to get t. We're going to subtract v from both sides. And we're going to divide by the acceleration. So we're going to equals minus v initial over acceleration. Yep, just like that. Okay, so then we just plug it into these different things, right? Here, turns out we don't even need the, well, we do need the mass. Why do we need the mass? Because this doesn't tell us the acceleration, does it? It actually tells us the force, but what does tell us acceleration? What tells us acceleration is what happened to my whiteboard? There it is. Okay. Okay. So force equals mass times acceleration, right? And they have told us the force, and we want the acceleration, so we solve. We get acceleration equals force over mass. So this is the equation you need to apply in each part of this problem first, and then once force over mass, once you've solved the acceleration, then you put it into this equation, right? With the initial velocity and figure out time.
What do you use for initial velocity? Do you just like pick a number? Does it matter?
Yeah, you can pick any number. You can pick a number. You can pick 1. You can just call it v. But in the end, what's going to happen is the acceleration down here is going to be the thing that matters, because it's going to be something over a number. The bigger this number is, the smaller the time is going to be, because the number on the top always stays the same, right? So then you'll just solve for t equals v over numbers, and then that biggest number on the bottom is going to be a big deal. And all of these accelerations are going to be negative because all the forces are negative, right?
Yep.
So that's why this negative sign is on this equation. Any other questions?
I had number 9.
Okay, we'll do number 23 first, and then we'll do number 9.
Okay.
Complete the reaction for each action-reaction pair. Oh, we love these ones, right? So these ones, you kind of take the first noun and the last noun, you make them switch places, right? If your head bumps the ball, then what does the ball do to your head? The ball bumps your head. And it's pretty much as easy as that. If your bat hits the ball, then the ball hits the bat, right? If your hand touches the nose, your nose touches your hand. So it's just opposites of each other. If the rocket pushes the gas backwards, then the gas pushes the rocket forwards. And so on. And number 23, you said?
That's number
9.
Oh, sorry, number 9. We did number 23.
If the only thing I got wrong in that was a typo.
Yeah, you can send me
Instead
a.
of nose, I put N-O-E-S.
Yeah, you can go ahead and put an email to me. That's fine. All right.
I did the work and I tried 2 different answers, but I wasn't getting it, I guess.
Okay, so the average acceleration. Remember, what is the definition of acceleration? The definition of acceleration is the change in velocity over the change in time. And on this particular graph, what do we have? We have force versus mass, right?
Couldn't you use the force net equals mass times acceleration?
Yes, you can.
Which one are you guys on?
We're on number 9. Calculate the average acceleration of the object from the graph below. So we have mass, I think, yeah, you can do that. So I would do that where you have a definite point, like right here. I mean, these points right here are pretty definite, so it's not bad. So at 1, for example, you have a force of 8 and a mass of 1. So the force divided by the mass is going to give you 8, right? And then you have over here you have a force of 12. This is minus 12. So you have a force of minus 12, so it's minus 8, minus 12. So you have a force of minus 12 over 2, which is 6. And then minus 16 over 3, which is 5 point something. And then right here is minus 20 over 4, which is 5. So that, and then over here we have minus 24 over 5. Which is, what is 24 divided by 5? 4 point something. And the average for that is actually, let's see here. It's obviously, I think what you can do is take your first acceleration and your last acceleration, and this is kind of making a little bit of a step from our kinematics chapter, where we took the average velocity, be your initial velocity and your final velocity divided by 2. And since it's a constant change in acceleration between here, since this line is straight, I think that we can do that, except that this is a change in mass, not in time, so that's kind of weird. But that's what I'm going to do anyway. So essentially I'm going to take the negative 4 over That can't be it because that's over 0. The only other way to do this problem that I can think of is to use calculus, but we don't have calculus under our belts. You could do an averaging integral here, but we don't know how to do that here. So I think that this question has to be erased. Did anybody else come up with an answer that they got right here?
When I tried to open it just now, I popped up an error message. It wouldn't let me look at it. Remember which one again? Number 9? Try it again.
It's number 9.
Nope. Syntax error. Unexpected code. Very much code.
I think I'm going to erase that one from the assignment. Because I can't think of another way to do that besides using... I didn't notice the graph had force on its x-axis. I thought it had time. Because that would be a great question for if time was on the x-axis, but it wasn't. That was number 9, Cassie?
Yeah.
What's that? You can open yours? Probably not
Number
now.
9 was easy.
What did you do?
I got one that was 1 by 1 for the force times mass, and like the average is 1. The average acceleration is 1. And I got 1.
Let me look at your chart real quick here. What's your question? You had 6 over 2. I'm going to take that out of it anyway, because I think that the chart is wrong. To me, it doesn't make sense mathematically. I'll have to look at that one more closely. But I'm just going to take it out for now because I don't. Even if it's right, even if it's something you can do without calculus, which I'm still not convinced you can. I don't think I like the question there with force on the y-axis and mass on the x-axis. So I'm just going to take it off.
Isn't that one just slope though?
If it's velocity and time, it's slope.
But the acceleration, my acceleration, I seriously just calculated the slope of the line, and that was the correct answer.
Yeah, and that's what he did as well. But
That's the correct answer, but you're thinking that shouldn't be the correct answer.
that's how, yeah, I'm not sure if it is.
Okay.
And like I said, this is just being written and just being done now, so there's going to be a lot of things to think about here. So,
I have just a quick question on number 20.
yep.
Why would it not be C or E, I guess?
Okay, so we ran out of gas. That means we don't have any force pushing us forward anymore, right?
Okay.
So it can't be we don't have any force pushing us forward. So it can't be C because there's no applied force forward. And it can't be E because there's no applied force forward because our engine just stopped, right? So it can't be any forward force. C and E are out.
Okay.
But we also have to have some frictional force because we're coasting to a stop. So it can't be A because there's no frictional force there, right? And it can't be D. And B has the frictional force, and it also has gravitational and the normal force. So B is the only one that makes sense. The gravitational force is the Earth pulling the car down. The normal force is the Earth surface pushing the car up. Preventing the car from falling through the Earth's surface. And then the frictional force is what slows it down. Any more?
Yeah.
I haven't done the last few questions yet, so.
On number 4, I can just read it. It says a 16 kilogram brick and a 1.6 kilogram book are dropped. How many times greater is the force of gravity on the brick compared to the book? It's the same on both, right? Or is that a trick question?
It's another trick question. The acceleration that gravity exerts on everything is the same. In other words, everything accelerates the same amount.
But it's not the same.
But it has to pull harder on bigger objects to make them accelerate. Don't you have to push harder on a bigger object to make it accelerate?
Yeah.
So the bigger object has to be forced more to accelerate the same amount.
Okay. That mind-boggling, but we'll go.
Well, think of it this way. If it's not the Earth pulling on it, and you had to pull on it to accelerate them the same amount, and instead of pulling them downward towards the Earth, you're pushing them across the room. And one of them is a pencil, and the other one is a brick. Which one do you have to throw harder to get it to go across the room at the same acceleration? The brick, right? It's the same idea, except in horizontal motion, right? Okay, so Cassidy, which ones did you want to look at? Are you there, Cassidy? I think we lost Cassidy. She's still connected, it looks like. Cassidy, did you have any other questions you want to do? Now, do any of you want more time on this homework? I'm assuming you do.
That would be great.
Yeah, I'm here, sorry.
That's okay. Right now I'm just changing the due date. What day is best for you guys to have time? I assume people don't want to do homework on weekends. I never wanted to.
If I need to, I can.
Do you guys prefer to have it do Friday or Saturday or what?
We do Saturday.
I would like Saturday because my days off are on the weekends.
Okay.
So.
Available until Saturday. Let's see, that would be the 10th. All right. That is done. Did you have any more questions on chapter 4 homework that you want to ask, Cassidy?
I ran to grab my notebook. Not that I know of. I should be okay. If not, I can send you an email. But
Okay.
I do have a question about the lab.
Okay.
I was trying to do my calculations, and something wasn't working out for some reason.
Okay, which part?
I'm looking for my stuff. So when you predicted how far it would go, were you supposed to like calculate it with measurements and the formulas?
So the measurements that you should have when you're calculating how far it will go, first of all, from the first experiment, you should be able to figure out how fast it's moving when it leaves the launcher. Did you get that?
Yeah, but okay, so my distances and like my lengths were so small. They were like 0.5 meters or so.
That,
Um,
that should be
so,
sufficient.
okay, so then I do those calculations for the horizontal only.
So yeah, it's let's go through it really quick just to make it clear here.
Well, I ended up getting with my calculations 6.98 meters per second for my x,
Okay, that seems reasonable.
and then of course 0 for my y.
So you have a 6.98 meters per second coming out when you shoot it horizontally, right?
Yeah.
That's when you're shooting it horizontally. Now, once you move it to an angle, it's still going to come out at 6.9 meters per second. But now that has to be split into two, because now you're shooting at an angle. Some of it's going upward, some of it's going downward. So now you're in the second part of the experiment, your x velocity is lower because part of your original velocity is becoming y velocity when you angle it upward. So now your hypotenuse, or your overall velocity, equals 6.9 meters per second, or 0.69. You said 0.69, right?
No, it was 6.9.
Oh, 6.9, okay. That sounds reasonable also. But anyway, 6.9 meters per second. But now your velocity at this angle, whatever you were able to calculate, is 6.9 meters per second. But some of it is going to be y velocity, some of it's going to be x velocity, and you need to calculate that. For this y velocity, you're going to get 6.9 times the sine of your angle, whatever you got. Were you able to calculate your angle?
Yeah, I have my angle. It's like 24.78 degrees.
Okay, and then for the x one, it'll be 6.9 times the cosine of your angle. Now, this is where you split these two into two different problems, the x problem and the y problem, right? Usually we do the y problem first because usually we're going to use the y velocity along with our initial height and our final height, which is going to be the ground, to calculate our time. So we're going to use y.
Yeah, I calculated. Are we talking about the angle one now?
Yeah. So
Yeah. So that was my question. So I got to that point.
did you calculate the time?
No, because I got stuck trying to fill out the equation with my numbers.
Okay, so that's the hard part right here. So that's what we're going to do right now. So the things that we know are we know the final y. What's the final y?
0.
So your ground is 0.
Yeah.
Okay. So the final y is 0. Your initial y, where did you launch it from?
0.15.
0.15, and that's including the height of the ramp?
Yeah. Because it said start from 0 at the top of your table.
Okay, so if 0 is at the top of your table, then your final is not going to be 0. How high is your table from the ground?
I'd have to go measure.
Because that is going to be, what's going to happen is here's your ramp, here's your table, and here's the ground. If this is your 0 point right here, and your table is, let's say, 15 centimeters or something like this, then the ground is going to equal your final, which is going to be negative 15. It's 15 below 0.
Okay, that makes sense.
And then this one is going to be however high above 0. So your initial is 0.15, your final is going to be negative something below 0, so it's not going to be 0. And in the end, you're going to plug those into the equation that says the final y equals the initial y plus your initial velocity in the y direction times t.
That's where I got stuck.
This one comes from here.
Okay, when I was reading the packet, it was saying to use velocity initial, so that's what that number is.
That's correct. Yeah, this is the initial velocity in the y direction. Comes from this guy right here.
So that kind of confused me because I calculated it with the horizontal as my velocity of x.
Yeah, so when you were shooting it horizontally, that was your x velocity. But when you tilted it at an angle, it gave it that same velocity but at an angle. So then you had to split the velocity into a new x velocity and a y velocity.
That's why you use the trig.
That's correct. And then you subtract off the 1/2 times g times your t squared, and you solve this equation for t. Once you solve this equation for t, whatever you get, then you use it over here in the x to see how far it's going to go in the y direction, in the x direction, because in the x direction it's just going to go a distance x, which is going to equal the velocity in the x direction initially, which is this one right here, times the time that you get from the y direction.
Okay, so I'll be able to do that now. Thank you.
Okay, any other questions?
So then it goes back to my prediction. Were we supposed to calculate, or were we supposed to just say, nah, I think it's going to go this way?
This is your prediction right here. All of this stuff that we just did is your prediction. This will give you your predicted position finally on the ground from where you launched it. Your
But
horizontal.
So but we already launched it, but I already launched it, and
That's okay. If you launched it first, it doesn't matter. You can still calculate where it should have gone using this.
so we don't have to find calculations with the data we did get.
No, with the data that you did get, the distance that the ball landed, you're going to compare to this, and that's going to be your comparison.
Oh, okay.
The only launch that you use for your prediction is the horizontal launch that we did over here.
Yeah.
That's the only data that you took that you used in your prediction. Everything else you just measured and put into the prediction, calculated the time, calculated the distance it was going to fly, and then you went ahead and launched your experiment.
Okay. All right. Thank you.
Anything else?
No, I'll finish my homework, and if I have any questions, I'll email you.
Okay, I'm going to go ahead and sign off, and you have a good one. We'll see you next week.
You too. Thank you so much.
No problem.
Have a great day.
You too. Yep.
Could you look at the one, please?
Number 10.
Yes, please.
Okay.
Okay, so it talks about how inertia applies to, I got the first part right, it says inertia applies everywhere and to all objects. If an object has twice as much inertia, it means it has twice as much force, and vice versa. Force is wrong.
What is it that creates the inertia? Why do things have inertia?
Acceleration,
Nope.
motion,
Nope.
force.
Nope. It's in the book. I don't have my links to the book in these questions. I need to get those in there.
I looked at the chapter that was on inertia.
Let's look at it again really quick. It's not obvious necessarily, but it is there. The property of a body to remain at rest or remain in motion is called inertia. The inertia of an object is measured by its mass. Mass is the measurement of inertia. So if you have twice as much mass, you have...
Yeah, inertia is the measure of how much it takes to get to change, right? Isn't it?
Yeah,
So that's like twice as much mass.
that's correct.
Okay, so then the one that has the greatest inertia is the one that has the greatest mass.
Correct.
Okay. 16.
16?
Yes, please.
Nellie Nugent. So,
since she weighs whatever the amount of newtons is, since each
400.
row that's carrying her will each row have half of her weight on it. Would that be the tension?
yes.
Okay. And the net force on Nellie, since she's not moving, would be 0 newtons, right?
That's correct. Nellie Newton wishes to be a gymnast and hangs at rest, as shown in the diagram below. Nellie weighs and determine the force of tension in one of the groups. I think I'm just going to start altering these questions as I go to make them work better. I would fill in the blank shown below. Assume that her weight and distributed evenly to both. So, 16. All right, now that should read differently.
You see the link here, and specifically part
24.
3. Yep. And if we look at A2. Okay, so for A and S, for just what is the net force on the box? So since it's moving in the same direction, it's add the two forces, right?
Yeah.
And then you have the direction. And part 2, we just use the formula for acceleration, which is the net force over mass.
Yep.
And then on part 3S, if the object is moving, so on mine, the object's moving to the right. And it says if the object is moving left and then experiences the acceleration we found in the previous part, what will happen to the motion of the object? Isn't that dependent on how fast it's moving that way?
No. They're not asking what happens. What happens. They're not asking what the end result is, a year from now. They want to know what happens to the object right then. So if it's moving to the right and it has an acceleration to the left, it's going to slow down, right? If it's moving to the right and there's an acceleration to the right, it's going to speed up. Does that make sense?
Yep.
So that one I would change to, what number was that?
The one that I was just on?
Yeah.
That was 24.
24? What is the net force part 3? The object, acceleration from the previous, what will happen to motion object? What will happen to motion object immediately after the force?
Mr. David, on number 25, it gives you the force and the acceleration, and asks for the mass. And the units would be in kilograms, right?
25. An object is accelerating at 20 meters per second north, speed net force on 6 north. What is the mass of the object?
That would be in kilograms, right?
Yes.
Okay. And then it has no direction because it's a scale.
Yes.
Awesome.
If a question, answer. Oh, this is confusing me. Mass acceleration and north southeast direction. Where are you pulling?
We look at number 26 as well. These last couple of sheets, last 5.
26.
Yes, please. Okay, so the normal force would be, in yours it would be 26 newtons, right?
Yep. Because it's at rest, it has to cancel out the weight.
That's what I thought, and then the direction of the normal force is up, so it's counteracting gravity.
Yep.
Okay, and then the next one that is in kilograms, you have to find the force.
That's right.
Okay.
That's the mass. You need to calculate the weight. And
Calculate
then-
the weight or calculate the acceleration.
You use the acceleration to calculate the force that gravity is pulling on, which is the weight.
So it was net force equals mass times acceleration.
That's correct. And you use 9.8 for your acceleration. How you doing, Packer?
Well, good. I'm a little bit frustrated with a couple of problems, but nothing too bad. I just want to come back and then fresh.
Do you have any questions?
Well, I'm having some issues with 17, but I think that's just me. But
What problems are you having with 17?
I just made a couple of attempts at this problem, and I'm sure I'm doing it right, or never right, but I'm just not sure. But it's not a game.
What are you doing?
Calculated acceleration using force and mass.
So the total acceleration in the box, right?
Yeah.
So first of all, we start with calculating the net force, right?
I already did that. I just had to calculate acceleration.
So how did you calculate the acceleration?
I divided 14 by 3.
So 14 was your overall force?
Yeah.
And 3 was your mass?
I forget what they changed. That is how you calculate acceleration, right?
Yes.
So
2 is
14 divided by 3 is 4.7.
Sounds correct-ish. Yeah. 4.7, yeah.
So I go into my thing, put in 4.7, check it, and it says I am incorrect.
Well, let me look at your particular problem here. Question. Which one is this?
17.
Gotta be kidding me. Try 4.67.
Okay, now it's accepting. I just went with significant digits. Alright. Yeah, I tried it a couple times and it was just going with significant digits and it was not giving me a correct.
Try 4.6.
I got 4.67 working.
I know, try 4.6. I just want to see if that works too.
Nope.
So it's requiring you to put in 2 decimals. Huh? I'll just change that to full credit.
No, because I tried it a couple times and missed it. And then, what time does this class officially end?
Officially, it's 6.
No, like, not. What date? I have to know for work.
August something.
August, so it ends in August?
Yeah.
August is something.
Yeah, why?
Dee wants to know. I think she wants to know if we can adjust numbers schedule to longer hours before.
Let's take a look really quick. We'll look at
Before I get back to
campus. I need to make a new homework assignment. I don't think I have one for chapter 5. Well, maybe I do.
So we're removing mics from the floor in the cafeteria today. So I think it's safe to say that my interest in that room has been waning.
Your interest in the cafeteria.